Okay, so moving on to the longer, wordier questions here. We see that this is a question about two functions acting on the positive integers n. Okay, so the functions f of n and g of n are defined for positive integers n as follows. So I can see here that f of n generates odd numbers and g of n generates even numbers, in fact, only sort of multiples of 4. Okay, so g of n generates multiples of 4, f of n generates sort of all the odd numbers. This question is about the set S of positive integers that can be achieved by applying in some order a combination of f's and g's to the number 1. For example, gfg1 equals gf of 4 equals g of 9, which is 36. Okay, that seems to make sense, yes. Okay, and they give you another example here for 67. Okay, so both of those numbers are in S because they can be generated in this way. So write out the binary expansion of 100. Okay, and they tell you what binary is. It's for sort of base 2, and they show how 13 can be written in binary. So let's do that for 100. The way that I usually do this is think of the smallest power of 2 that is less than 100, and then keep adding on powers of 2 until you get to 100. Okay, so the smallest power of 2 less than 100 is 64, and then the one lower than that is 32, so 2 to the 5. If you add those together, you get 96, and then you just need to add on 4, which is another power of 2. So we can write this as 2 to the 6 plus 2 to the 5 plus 2 to the 2. And you have to remember in binary that that you need a sort of 2 to the 0 part. So if I write this out as a sort of table, we've got 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, and 2 to the 6. So we don't have a 2 to the 0. We don't need to add on 1. In fact, you put a 1 in this column for any odd number and a 0 for any even number. So we don't need the 1. We didn't add 2, so we need a 0 there. We did add 4 though, so that's where we put a 1. We didn't add 8. We didn't add 16. We did add 32, and we did add 64. Okay, so there is 100 in binary. Okay, so show that 100 is in S by describing explicitly a combination of F's and G's that achieves 100. Okay, so we can kind of work backwards from 100 to get there. So what I would say is, because 100 is an even number, you have to have had applied G on a number to get 100. Okay, and in fact, we know what that number is. It's 25. If you put in 25, 4 times 25 is 100. So we could first say that G of 25 is 100. And then we've got the number 25. So 25 is now an odd number. So you could only have got to 25 by using F. So 25 is equal to 2n plus 1. Then n is 12. If you take away 1, it's 24. 24 divided by 2 is 12. So we could say that this is G of f of 12. Okay, and then repeating the process, 12 is a multiple of 4. It's 3 times 4. So 12 is in fact G of 3. So we can write this as G f G of 3. And the last step is, how do we make 3? Well, we have to do that with f because it's odd again, and 2 times 1 plus 1 is 3. So we can get there from applying f's and g's to 1. Okay, and that sort of combination is G, F, G, then F of 1. Okay, so that's your unique combination. Okay, so show that 200 is not in S. Okay, show that 200 is not in S. So we can probably think about it in exactly the same way as we thought about it up here. If you want to find a number which, maybe you apply g to it, well, you have to apply g to it because 200 is, again, even, then that number is 50, right? So g of 50 is 200, or you can think of it as inverse g applied to 200 is 50. But then 50, it is an even number, but it's not a multiple of 4. So there is no number, there is no positive integer n for which f of n or g of n makes 50. So you have to stop here. It's impossible to sort of carry on. At this point, though, if you were doing it like I have so far, I'm sure that you would have got these marks. It doesn't say you must use binary to do this, but you might be thinking, why did they make me do that thing with binary? So what we could do is we could see what f and g do to binary numbers, and it may help us solve the next few parts, and in fact solve, part 2 and part 3. So if I let's start easy just with the number 1. 1 in binary is just 1. If I apply f to 1, 1 times 2 plus 1 is 3. So that would give me the number in binary 3. 3 is just 1, 1. It's 2 plus 1. If I applied f to 1, 1, it would give me, so 2 times 3 is 6, plus 1 is 7. And 7 can be made of 1 plus 2 plus 4. So that's actually 1, 1, 1. Interesting. It seems that f might just add a 1 on the end of binary numbers. Okay, so it might increase the number of digits by 1 by sort of adding a 1 and shifting all those other numbers over by 1. So we can kind of see if this is going to work by considering a binary number n to be made up of 2 to the a plus 2 to the b plus 2 to the c dot dot dot. Okay, so these would be different multiples of 2 different powers of 2 that you're adding together here. These are some a, b, and c. So if you think about it, if the number a was like 13, it means you have a 1 in the sort of 13th place. Okay, actually I think it's the 14th place because you have a sort of 0th position as well. Okay, so if we consider what 2n looks like, 2n is just multiplying everything here by 2. So in fact, it changes everything to 2a plus 1 plus 2b plus 1, etc. Okay, so it'll do the same thing to c. And in fact, if you had a plus 1 on the end, okay, a sort of 2 to the 0, then it would make it 2 to the 1. So this would shift all the numbers over and add a 0 to the end. But 2 to the n plus 1 would, in fact, put a 1 in that last position that has a 0 in it when you multiply by 2. So the rule is that f adds a 1 onto the end of a binary number. Okay, so f adds a 1 onto the end of a binary number. What does g do, though? So let's just consider what 4n would do. That would in fact give you 2 to the a plus 2 plus 2 to the a, 2 to the b plus 2, dot 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 dot. Okay, so this is actually going to shift all the digits over by 2, and it's going to kind of append a 0, 0 to the end of these numbers. So you can think of that as if you did happen to have ones or a 1 on the end or a 2 on the end, so it's something that you need to add 1 or 2 to, so like 7 for instance, then multiplying 7 by 4 gives you 28. I think if you put 2 zeros on the end, that should work, right? So this is in fact 4 plus 8 plus 16, which is 28, so it did work. So you just sort of put 2 zeros onto the end of a number when you apply g to it. Okay, so this is going to be very helpful, I think. I think in fact we could show that that 200 is not in S, by considering the binary the binary code that encodes 200. So because you're applying this all to 1, so you start with the binary digit just 1, then you apply some combination of F's and G's to this 1. That will give you, so I'm just going to sort of go some combination. Okay, some comb. Okay, that will give you some combination of 1s and 0 zeros. Okay, but you can never get a single you can never get like a single 0 on its own, and yeah, you can only have sort of these sort of strings. Okay, so if we wrote out the expansion of 200, I'm willing to bet that it would probably have a 0 on its own at some point, and that's another reason why you can't have 200 in S. Okay, so the next part, it says show that if n is in S, then there is only one combination of F's and G's in order to achieve n. So for example, 67 can only be achieved by applying G, then F, in that order. Okay, so this is kind of proven by what we've been talking about here, by the fact that every unique combination of 1s and 0s encodes a different number in binary, and well, a different number, period, really. And so if you apply G or F at any point, you set what that number is going to be in that order. Okay, so if you apply, so this unique combination here is applying to 1. So we started with this 1 here. Okay, so we applied F, then G for those 2 zeros, then F, then G, then F, then F, then F, then G, then G, then F. So you could only get that order from applying F and G in that specific order. So each unique combination of F's and G's gives a unique binary number, which means that there's no two ways of getting to any number in S. Okay, so yeah, I think that answers this part of the question. It may be a bit harder to get there without using the binary, but I think it's possible. What you could say is that basically every number is either even or odd, or I guess you could say it's either a multiple of 4 or it's odd if it's in S. So if you start with a certain number, it's either even or it's odd. You have to go down one of these branches. So that means that if you start with this n in S, then if it was even, you can apply inverse G. And if the number then was odd, then you'd have to apply inverse F. And there's only sort of one way that you can go sort of down this branch to eventually end at 1. Okay, so it's the same as saying there's only one way from 1 to get to n, because at each point you either have an even or an odd number, and so there's only one option to kind of apply inverse G or inverse F from there to get to n. Okay, so the next part seemed to get a little bit harder. So let UK be a number of elements n of S that lie in the range 2 to the k up until, but not including, 2 to the k plus 1. Show that UK plus 2 is equal to UK plus 1 plus UK. Okay, so it's like saying the number of elements in the sort of in the next section is equal to the number of elements in this section plus in the previous section. And actually, if we look at this range, I think this is actually saying the binary numbers of a certain number of digits. So let's just try k is, I don't know, 3. So we have this 2 to the 4. So this is in fact the numbers 8 up until 15 in non-binary, and number 8 is 0 for 1, 0 for 2, 0 for 4, 1. So that's a 4-digit binary number. the number 15 I think should be written like this. Yeah, I think that works. 1 plus 2 is 3, plus 4 is 7, plus 8 is 15. And then the number 16 would be with 5 digits. So you're sort of jumping into the next number of binary digits. So I guess the first thing to say here is that the elements UK can be written as, so we used k equals 3 here, so there are k plus 1 binary digits to any one of the elements in UK. Okay, so there are k plus 1 binary digits for any one of the elements in UK. But then to create to create the binary digits with at least one more binary digit, you would need to apply f to that. Okay, so if you think about it, if you have an element in UK, so any element in UK, if you apply f to it, you get an element in UK plus 1. So, and also if you have any element in UK and you apply g to it, you get an element in UK plus 2. And as we said, there's only sort of one unique way to get to any n in S, then that makes perfect sense. This here makes perfect sense. It's basically saying that the elements with k plus 3 binary digits, okay, can only be made by applying f to elements with k plus 2 binary digits, or applying g to elements with k binary digits, okay, or sorry, k plus 1 binary digits, okay. And the elements with k plus 1 binary digits are UK. The elements with k plus 2 binary digits are UK plus 2. And the elements with k plus 3 binary digits are UK plus 2. Okay, so as there's only a unique way of getting there, you have to have gotten there by applying f or g to the elements of the sort of in the ranges below. Does that make sense? So yes, this all relies on you having got the previous part correct by considering it in binary as adding sort of 2 digits onto the end. Okay, so the next last part of this question is asking for numbers up to 2k plus 1. Okay, so I think usually when you've got a sort of extra part here, you're going to rely on the solution to the previous part. So I'm going to sort of state this as true, or sort of, if you didn't get this part, if you didn't get part 5, in part 6, I guess you can assume it's true. Here we've proved it's true, or we've sort of stated a very good argument for it being true. So we can use that in part 6, and we're probably going to have to use it in part 6. So if we write out a sort of expansion for sk plus 2, we could say that is u0 plus u1 plus u2 plus dot dot dot, and I'm going to go with uk minus 1 plus UK plus UK plus 1 plus UK plus 2. Sorry about that, running out of room there. Okay, so if I do the same thing for SK plus 1, it's always nice to write these things out in full. If you're very accomplished at using the sort of sigma notation, you could do that, but I think writing it out in full is sometimes a little bit more useful for me. UK plus 2, dot dot dot, and then you have UK minus 1 plus UK plus UK plus 1. Okay, so just looking at the ranges, you can see that if you add all of the ranges of U0 up to UK, you get SK, because the bound on the top is the same, and if you think about U0, that is starting from 1, okay, because 2 to the 0 is 1. So So all of these expansions are true. So I can see in the thing I'm trying to prove, it's got an sk plus 1, an sk, and an sk plus 2. So I'm going to have to write sk as well. So that's u0 plus u1 plus u2 plus dot 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 uk minus 1 plus uk. Okay, and so when I add sk to sk plus 1, I can always use this rule that uk plus 2 is equal to uk plus 1 plus uk. Okay, I can use that rule. That's kind of taken as true for this next part. So if I do that, if I add these two together, if I added, I guess we call that equation 1. Let's call that equation 2. If I added 1 and 2 together, I can see there's kind of a pattern here. If I add u0 to u1, then that would give me u2. Okay, u1 to u2, that would give me u3. And if I carry on doing this, so I'm going to get u4 somewhere here. Okay, if I carry on doing this all the way up, so that's going to give me UK. This will give me UK plus 1. And this last one will give me UK plus 2. So what am I actually missing here from UK plus 2? I've still got this this U0 here, sorry. So if I look, the only number I'm missing here is U1. So what is U1? U1 are the numbers in the range of 2 to the 1 up to n 2 to the 2. So they start at 2 and they go up to 3. Okay, so the numbers 2 and 3 in binary can be written as 1, 0, that's 2, and 1, 1, that's 3. And in fact, 2 can't possibly be in the set S because it's made up of a single 0. We're not allowed single zeros. We add on 2 zeros or just 1s. 1, 1 is 3, and that certainly is in the set. You can think of that as 2 times 1 plus 1, so it's f applied to 1. So u1 is in fact equal to 1 because there is only one number in that range that that gives that gives an element in S. So we can say that sk plus 2 is equal to sk plus 1 plus sk plus u1, and that is equal to 1. So that gives the expression that you're looking for in this last part.